we're just going to briefly go through and look at the type of things that we're going to talk about in subsequent lectures related to nuclear power, describe what nuclear fuel is, what does nuclear power look worldwide, and how's nuclear energy been implemented, and what are the types of reactors that we need to look at and learn how they operate. Everything was based on uranium. I was talking in the previous part about uranium and U-235 as a primary element that we think about when we're looking at nuclear fission, and we'll look at uranium in more detail in the chemistry section. But uranium as an element was discovered and separated and recognized as a separate element in 1789 by Martin Klaproth, and he was essentially looking at pitchblende, which is an ore and a compound that's been used for a long time and been recognized as a long time as having lots of different properties and things like that. In fact, all the way back as early as ancient China and Rome, people were using pitchblende and essentially extracting the uranium from that to make into glass, because it forms a lovely green pigment. And in fact, what we see here is that this particular glass, and you can recognize uranium glass from other green glasses in the fact that if you shine a UV lamp on them, they fluoresce. Uranium is quite a common element in the lithosphere, in the rocks that make up the Earth. There's almost 200 or so minerals that can contain uranium in measurable quantities, and of course what happens is that those minerals erode with rainwater, and that uranium gets flushed through rivers into the sea. So there's actually in terms of mass, there's a lot of uranium in the seawater, although the concentrations are very, very low, only about 2 to 4 micrograms per litre. When we're thinking about actually uranium mining, and we're thinking about actually extracting that uranium to make into nuclear fuel, of course, we want an actual uranium ore, and the most common ore that we look at for mining operations is uraninite, and that's essentially high-grade uranium dioxide, uranium a compound of 2 oxygens and 1 uranium atom. So the oxygens are 2 minus, and so therefore that the uranium's in a 4 oxidation state. So that's the most stable type of oxide and most common oxide. Of course, you can find other ones as well. So if you think about this pitchblende ore again, that's a mixture of oxide states, uranium trioxide and uranium dioxide, which tells us that the chemistry of uranium is that it can exist in different oxidation states and still be stable. As I mentioned when we just briefly introduced Marie Curie, she was extracting radium from pitchblende and from other uranium salts, because as uranium radioactively decays, it goes through a decay chain, and one of those elements with a long-lived time, a long half-life, is radium. And so she was using uranium as a source of radium. So what we want to do is convert that uranium into a usable quantity, and so we can put it into fuel after we've purified it chemically and perhaps enriched it in U-235 so it can sustain a chain reaction in our modern reactors. What we do is we convert it to a ceramic pellet, and that's about 10 millimeters in diameter and about 10 to 15 millimeters long. And we stack a number of these pellets into a metal tube, a fuel rod, and we seal that in, and then we stack all those metal tubes, those fuel rods, and we put them together into a large stack held together with grids. And in this particular case, it's probably about 18 of those by 18, and that's referred to as a fuel assembly. Now they are this shape and this configuration because what we're looking at is very good heat transfer. So the chemical engineers among you will recognize something like a tube bundle from a heat exchanger, which is very analogous. So they're on a particular tube spacing, and this is from a pressurized water reactor, so it's cooled with water, and the water can flow through that and take the heat away. And what we have with pressurized water reactors is we have a stack or control cluster of rods there, and these rods are filled with boron nitride, which is a neutron absorber, and we can use that to control the flow of neutrons, the neutron population, and control that criticality. Now, fuel assemblies come in different sizes and shapes depending on what the reactor is. There's a hexagonal array, a VVER, which is essentially Russian for pressurized water reactor. essentially doing the same job as this, but in this case it's hexagonal. They're more closely stacked together. In the UK, we have an advanced gas reactor, which is actually a reactor that uses carbon dioxide as a coolant and carbon as a moderator. That's a circular fuel assembly. The rods are about 1 meter long, similar diameter though, about 10 millimeters in diameter, and the pellets are about the same as well. And also in the past there's been a Russian designer, one called an RBMK as well, so that's a gas cooled reactor there. Now worldwide, if we go back to one of the most recent censuses that was taken and published, as of May 2016, there were about 30 countries operating civil nuclear power programs and upwards of nearly 450 operating reactors. And if we look at the geographic spread of those, we can see Europe, quite a lot in Western Europe, Eastern Europe, that would be Russia and the old Eastern European states as well. North America has a lot of reactors, primarily in the US. And interesting enough, this green here is the number that were under construction at the time. You can see there's a lot of new build going on within the Far East. Primarily then would have been China and South Korea, and pre-Fukushima, Japan. Now let's just think about those countries on a different way of showing that in terms of how much electricity within that country is actually generated by nuclear, the share from 0 up to nearly 100%, and we can think about the actual number of nuclear power plants that are there. And we can see a lot of the countries are clustered around about the 1/4 to 1/3 of the electricity is generated, and upwards of perhaps a couple of dozen nuclear power plants, although we get a couple of outliers, interesting enough. So we've got an interesting outlier here where there's 60 nuclear power plants within that particular country, and nearly 80% of the electricity, the vast majority of the electricity, is generated by nuclear. And likewise, we've got here nearly 100 nuclear power plants, but only about 20% of the electricity. It's interesting to see what those countries are. I wonder if you can guess. So that one's France. And France had a policy in the 1970s that it would generate the majority of its electricity from nuclear, because it didn't have resources like coal or gas. That one's the US, very big country. Even though it's got 100 power plants operating, generating nuclear power, the actual energy demand of the country means that they only represent about 20%. Some interesting other countries. There's another country that uses a lot of its power, nearly 40% of its power comes from that, but very few nuclear power plants, so it's only a small country. It's Belgium. They've very much closely aligned themselves with the French in terms of developing their civil nuclear industry. We've got a country there that has over 20 nuclear power plants, but very little power in terms of the share. That's because it's a very big country. That's India. We've got a country there that, well, as of a year ago, had over 40 nuclear power plants, but had 0 power. That's an interesting statistic there, because actually what that is Japan. And the reason it had 0 power is because it had shut its power plants down while they essentially recovered from the Fukushima accident. If we look at pre-Fukushima, Japan had nearly 1/3 of its electricity being generated from nuclear power, and had one of the biggest fleets of nuclear power stations in the world. And there's the UK. Got about 20% of our electricity as it stands at the moment, and we've got about 14 nuclear power plants. We've got 13 AGRs and 1 PWR. And when we look at all those power plants and all the way they've been implemented, we think about the different generations from the very first prototype reactors in the 1950s. In the UK, that was Calder Hall, which was our first gas-cooled reactor. In the US, there was the original water-cooled reactors. We built our first generation of proper commercial power reactors, our Magnox fleet, and the first generation of water-cooled reactors in France and America. We then went into the 1990s, and we've now built and operated our more advanced water-cooled reactors. which is the majority of the fleet around the world, and also our advanced gas reactors in the UK. And now we're thinking about in the UK of building the next generation in terms of more evolutionary designs of those water-cooled reactors, which is Hinkley Point C, which is the big construction project going on in the south of England. There is a shift though, because when we come to the next generation of nuclear power stations, which are due to be built in the 2030s and onwards, Generation 4 as it's referred to, these are revolutionary designs in the fact that they look very different to these, and in some cases they are what called fast reactors. So remember I was talking about moderating neutrons and reducing the energy to what was referred to as thermal levels. All these reactors are thermal reactors, whereas some of these will be fast reactors. They take those neutrons, they don't need to moderate them, and the neutronics is such that they can cause fission, and they can use all of those neutrons for fission, and they can use more isotopes than U-235, so therefore they're much more efficient. Now, to go with those particular reactors in the UK and around the world, like France and to a certain extent early on in America and Japan, we built other facilities as well. So in Generation 2 in the UK, we built our first gas-cooled reactors called Magnox, and we had reprocessing plants that recycled the fuel and took that fuel and treated it. And likewise with Generation 3, we built reprocessing plants that could reprocess a different type of fuel that was based on the uranium oxide, and the French did the same. There's a picture of a thermal oxide reprocessing plant at Sellafield there, and that's shut down last year, and they've been operating since the early 1990s. And later on in lectures I'll take you through the processes that we use to recycle fuel. As we look to the future, we think about different types of reactors that may be built. The AP1000 is an advanced pressurized water reactor that was developed by Westinghouse in the US, but the Koreans and the Chinese are building versions of those. And the EPR is an evolutionary pressurized water reactor, which is the type that's being built at Hinkley Point C. And we'll think about different facilities to go with that. So the French operate a large reprocessing complex at Cap La Hague. There's a picture of it there. And they've got modified reprocessing plants that can take different types of fuels from these reactors. And we're working on R&D programs in the UK, leads part of that, where we're looking at advanced processes that we may be able to have different types of products and different types of fuels in the future. And of course, as we move to the Generation 4 reactors, the fast reactors, this is a cutaway of that sodium-cooled fast reactor I mentioned, or I'm going to mention later. We do have to think about different types of processes because we may want to recycle far more of that fuel in the form of actinides, and by that I mean neptunium, americium, curium, because we can use a lot more of those elements as fuel. So those future reactors, those Generation 4 reactors, the Generation 4 International Forum, the GIF, has agreed that there'll be 6 types of reactors that we'll look at developing around the world. And to develop a reactor, it takes a long time, especially to get one to a commercial footing. And they're done on a collaborative basis as well because of the cost. So these are the 6 that have been agreed on internationally. We've got different types of reactor there, and Dr. Jar will take you through and describe each one of those. But the one that we're interested in mostly in Europe and the UK is this sodium-cooled fast reactor. And there's one being built in Europe at the moment as part of a European collaborative process that the UK is part of, and hopefully we'll have a demonstrator sodium-cooled fast reactor in the 2030s. We've done work in the past though. There's a nuclear site at the north of Scotland called Dounreay where some prototype fast reactors were built as well. Now they're all very different. You can see we've got some gas-cooled reactors there. This is water-cooled but works at higher pressures, supercritical. Got metal-cooled. Essentially, metal is very good at heat transfer fluid and can remove the heat because these work at much higher temperatures than the reactors that we have at the moment. And this last one here, this molten salt reactor, is very different because the fuel itself isn't in the form of solid pellets. It's actually fuel that's been dissolved into the coolant, and the coolant is a molten salt that circulates around. And so therefore that's a very different type of reactor system. And I'll describe that a little bit when we talk about the different types of reprocessing.